All right, so let's get down to it for today. I don't want to talk to you for very long because, again, most of the lecture stuff that happens is going to happen outside of class. But, again, for today, because you might not all have had a chance to look at the videos and to come to class with that.
Sorry, I just remember from the syllabus you mentioned something about response.
So before we get down to business and talk about antiderivatives again, let's just take a moment and refresh our derivative minds. Because after all, we don't know how to do something backwards unless we are sure we know how to do it forwards. And this happens in categories, because what you develop in Calc 1 is, first of all, a sense of how to take the derivatives of certain classes of functions. And those classes tend to start with the powers of x. So the derivative of the first power of x is 1, according to this. And what happens if I change the exponent on that x? So instead of a first power of x, let's suppose that I tweak this up a little bit and make it a third power of x. Something. So what has changed? Or how would you describe the process of taking the derivative of a power of x? Yeah.
You bring the power down and then lower by 1.
Okay. So you bring down the power. In other words, what are we doing with that exponent? Really, but other than bringing it down, what is actually... Right. So you're multiplying by the power, by the exponent, I'll say, is the first step. And then the second step is... Right. Decrease the exponent by 1. And that's how you take a derivative. So then how do you take an antiderivative of a power? You do that backwards. So let's suppose that I wanted to take the antiderivative of x to the 5th or something like that. What would that antiderivative look like?
It looks like you have to add 1 to the exponent as well as divide by the exponent if you're multiplying the derivative.
Right. In order to reverse this two-step process, we're going to do these two steps backwards and in the opposite order, right? So the first step that I'll do is the opposite of the last step from before. So let's call this negative 2 instead of 2. Instead of decreasing the exponent, we're going to start by increasing the exponent by 1. And following that, divide by whatever our new exponent is. So the antiderivative of x to the 5th would be x to the 6th divided by 6, indeed. Really, if I'm taking an antiderivative, I need one more thing in here, too. What's that? A constant. Why do I need a constant here? Well said, right. We put the plus c in front of any antiderivative because it's in recognition of the fact that if we were to take the derivative to go back the other way, that additive constant would go away. It would vanish. So, cool. So that kind of closes the book on powers of x, right? With a single exception. What's the one power of x that we can't do this with? X to the 0. So let's think about that for a second. What would the derivative of x to the 0 look like if we were to follow the same set of rules? Bring the exponent down and multiply by it, and then decrease the exponent by 1. What do I get? 0. 0 over x. But as long as x is not equal to 0, that's just equal to 0. But what is x to the 0 power to begin with? It's 1. So the derivative of 1 is equal to 0, true or false? Yeah, seems fine to me, right? So taking the derivative with a 0 power is not a big deal. The derivative of 1 is equal to 0. What about the opposite? Supposing that I have, well, I guess here's what I'm trying to get at. When we take an antiderivative, we end up increasing the exponent on x, whatever is up here, and then dividing by that new power. So where's the trouble here? Yeah. Right, the trouble comes from x to the power minus 1 over here on the right, if I'm taking the antiderivative. Then when I increase the exponent by 1, negative 1 becomes 0. Whoops, get a legible color in here, x to the 0. But then why is this an issue? Right, because this would require me to divide by 0, and dividing by 0 is a cardinal sin in mathematics. So in other words, this expression is kind of meaningless over here. By the way, one of the interesting themes of the second portion of our course is that division by 0 actually is meaningful if we understand it in the right way. But we'll come back to that in a week or two. For now, we just have to know that this x to the 0 divided by 0 is a nonsensical expression, and yet x to the minus 1 is something that we want to have an antiderivative for. So what is the antiderivative of x to the minus 1 if it's not x to the 0 over 0? Say again?
Infinity?
Well, x to the 0 over 0 would seem to represent an infinite quantity. But here's my issue with this. Let's suppose we just were to put together a graph of the function y equals x to the minus 1. So let's take a second and do that here. So y equals x to the minus 1 is a hyperbola. It looks something like this, right? And so this is a perfectly valid function that we might want to take an antiderivative of. So it's got to have some antiderivative. It's not going to be some infinite or undefined crazy thing. So what is the antiderivative of x to the minus 1? Natural log of x. In fact, there are some textbook authors that use this to define what natural log is to begin with. I don't think that's a great idea, but in some ways, it's as good an idea as any. Natural log of x. Of course, I need a plus c in here. And if I look at natural log of x, the graph of natural log of x, y equals natural log of x. I'm getting my colors all screwed up here, but graph is going to look something like that. Y equals natural log of x. There's a bit of a problem with this, though, because our original function graphed here in red is defined on what domain? Y equals x to the minus 1. What's the domain of that function? Right, so the domain of our original function here is all real numbers from 0 to infinity. Anything else? Where else is y equals x to the minus 1 defined? Negative infinity to 0, right? So again, if you're looking at a graph, one way of getting at the domain is just to squish the graph down into the x-axis and observe which portions of the x-axis are being covered. But which portion of the x-axis is not being covered here? Yeah, 0. So the domain of our function, x to the minus 1, is everything from negative infinity to 0 and everything from 0 to infinity, but not 0 itself. So it's really, if we write it in interval notation, it looks like this. Everything from negative infinity to 0 and everything from 0 to infinity, but not inclusive of 0. Anyway, my point in that is not just to remind you of how to think about the domain of a function, but also it means our antiderivative is missing something. That we would like our antiderivative to have the same domain as the original function does. But if we take y equals natural log of x, what is the domain of y equals natural log of x according to this? If we squish that onto the x-axis, how much of the x-axis do we get? We get 0 to infinity. We only get the right part. The part on the right side. Not the correct part, but the part on the right side. So how do we extend that so it also gets the portion on the left side? I want the piece from negative infinity to 0 to be included also. Anyone remember what the dodge is to make that happen?
Absolute value.
Where do I put an absolute value? like this. Where? Yeah. So let me just take a moment and just talk about what the difference is. If I put the absolute values around the whole thing, natural log of x, I end up making the value of ln of x always non-negative. And the graph of that would look like this. But that's not what we wanted, right? What that did is it took the part below the x-axis and it flipped it up. What we want instead is to take the part that's to the right of the x-axis and reflect it over to the left. So we need to make all the x's non-negative so that we can take the natural log of them. In other words, I want to put the absolute value bars on the x. What that does for us is it gives this natural log graph a second piece. It gives it a piece over here. And now we have an antiderivative. So starting to turn those Calc 1 gears again. And it's not, I mean, it's surprising how often this antiderivative comes up in calculus, and especially in calculus 2. So when you have the antiderivative of x to the minus 1, remember it becomes natural log of the absolute value of x. What's another way to write x to the minus 1 to make it more, in a fashion you're more accustomed to seeing it? What is x to the minus 1 really? 1 over x, exactly. And that's often the way that you see it in a problem. So rearranging that to x to the minus 1 is often the first step in reminding yourself how to take its antiderivative. Questions so far?
So ln x equals x to the negative 1.
ln of x is the antiderivative of x to the minus 1. So remember this. Yeah, there's a step here in the middle. But yes, the antiderivative of x to the minus 1 is natural log of the absolute value of x. And that more or less closes the book on antiderivatives of powers of x. So let's talk about another couple of kinds of functions we might want to take derivatives of.